Let's see if this is going to work. I'm not sure. Hopefully it will work. All right. So what is the inverse Laplace of this? So what you can do is you can do L inverse of f of s, which is equal to, which is represented as f of t is equal to 1.8 e to the power of.
Whoa, oh, wait. No, it's just the inverse, so it's e to the negative. It's just t.
It is just 1.8. Huh? It is just 1.8. So what is the? It is. Think about this. Think about it like this: s plus 0, right?
Right.
So what is the inverse of such a thing? E to the power of minus 0t,
Which would be 1.
which will be 1. Okay. So this minus
Negative
5
e to the negative.
e to the power of minus 2t plus.
I don't think it's just method. I think it's T.
Huh?
I think it's 1.8.
Yeah, how do you put a zero in there?
Oh, no.
Yeah, we were thinking we were at 1 over.
I think you're right. That square is T. Okay.
So minus 5 e to the power of minus 2t plus
Plus 40 over 9.
40 over 9 e to the power
To
of
the negative
3t minus.
I need a sheet.
10 over 3.
Is that minus?
Mm.
No, that's a plus. Both of them. So plus
T squared. E to the minus.
10 over 3 e to the power. Sorry, t e to the power of minus 3t. Got it? Huh? So this is how you write it down. Any questions, any doubts? We're not going to take a look at this again and again. So please be clear how we're doing this. It's fairly simple. You will be given a table. If you refer a table, you can figure out what the inverse of. See, what we're doing is we're splitting this into sum of partial fractions. So the next topic we're going to cover is transfer function. Do you guys remember transfer functions? Did you
Remember what?
transfer functions? You did your flight controls, right? Stability and controls.
Yes.
Was transfer function discussed in there? No. Now, when you're developing your differential equation or your model, as we call it, what is a model? You know what is a model?
A mathematical representation
Representation of what?
of a given system.
See, for example, you have this, right? So this is representative of a model, right? So what is this model? What is this? What does it represent? What is the relationship? There is some relationship here. You see the relationship. Do you see the relationship? Hmm?
Yeah.
What is the?
Our law back to what we talked about last time. Correct, and time relating.
Right, something like that. So what does it relate? See, whenever you develop a mathematical model, it has to relate something. See, when you want to, let's say, you want to evaluate some dynamic system, what do you want to know about that? What does a mathematical model help you do? When you develop the mathematical model, what is it helping you do? Why are you developing the mathematical model of any physical system? Or a dynamic model of any physical system?
Understand how that system, I guess, will operate in a series of time.
Right. Or in other words, what you're trying to understand is, if I provide a certain input to the system, what is the output going to be? Right. That is essentially your goal. You want to understand, if you provide an input, what is the output? Can you predict the output? You don't want engineered systems which will behave randomly, right? You want some understanding of, for example, if you press on the pedal of your car, you want to know how far it's going to accelerate. You can develop that as a mathematical model and provide that input and see how it's going to react. The transfer function is something similar. So I'll give you the definition first. I'll give you my definition. Transfer function of any system is the ratio of output input. Okay. So if you look at here, this is a system. Okay. So this ratio you are seeing, this is although this is a Laplace transform, we're going to use this notation all the time. Does this make sense? No? Little bit? So what is C of S? C is the output or Laplace transform of the output. R of S is the Laplace transform of and G of S is the transform. And keep in mind, these are notations. You should understand notations and what the actual system is. Actual system is going to be something like this. This is the mathematical one. This is just a notation. Okay. So let's take a look at an example. Let's take a look at an example. If you are given, let's say, find example. Find the transfer functions of d over dt of c plus okay. So you're given this equation. This is a differential equation. Okay. What is the output here? Huh? Can you identify the output? Huh? C of t. Just look at this. It's this the output is in this is the Laplace transform of C of t. Okay. What is the input? What is the input over there? R of t. Okay. So what is the Laplace transform of this? How do you represent the Laplace transform? C of s. Capital C of s. And how about this? Now if you take the Laplace of this, and it's easy to take the Laplace, d over dt plus of S. Again, this is very clearly, huh?
So I can't turn off the program. I really can't.
This, you can see this in the tables, okay? So how do you extract out C of S? C of S is C of S over R of S is 1 over S plus this is the transfer function. Any doubts of how to get to the transfer function? We have lab session today at 2 o'clock, and we'll meet here at 2. Okay? Yeah.
This first lab is quick, right?
2 to 5.
Today?
Like an hour.
What I'll do is we'll do a little bit of prep for next class. So these are what we are going to discuss. We're going to discuss 2 types of systems.
Yeah, I'm gonna be in my Germany, man.
First one would be electrical systems. Mechanical or aerospace systems. Okay. So when we're discussing electrical systems, please review this.
You want to review this before lab or before Tuesday?
Before Tuesday's one. Okay. We are not going to discuss this in very detail. So you need to figure this out on your own. And you guys have done this. So that is the reason you need to go back and look at what Kirchhoff's current law is, Kirchhoff's voltage law is, and Kirchhoff's current law and its application. So we're going to discuss nodes, loops, right? You remember those? So you have to go back and review how to apply Kirchhoff's current law at nodes and how to apply voltage law for loops. And with regards to mechanical and aerospace systems, what you're going to do is, this is 1. We want to review Newton's laws of motion, okay? Particularly, second law. And spring mass damper systems.
Question, I'm saying this, but at the input, in the middle of the board, where you have Laplace RMS, RT.
John is paying attention.
Yeah, I am paying attention. Thank you. Thank you.
Second part of that question. DDT, is that, okay, so is that what you did the S from the second line? Go up 1 line? Okay.
Right, it is, so if it is d over dt, it is s. If it is d square over dt, it is s square.
Repeat that, I'm sorry, I didn't hear.
If it's differentiation, the first differential is s. If you take the double derivative, if it was d square over dt square,
D square or
this would just be s square.
okay.
It's that simple. And if it is just some function, it's just its Laplace. Okay. You see that in the table which will be made available. And this you just take that c of s common. Okay. You take c of s common. So in brackets you have s plus 2, which will go to the denominator. Now make sure you review these. This textbook has all of that. If you want, you can go back to your physics textbook and review this.